Hello students, today we will be discussing molecular rearrangements. Our main focus will be on Wagner-Meerwein rearrangement, Wolff rearrangement, Benzilic Acid rearrangement, Beckmann rearrangement, Lawson rearrangement, and Claisen rearrangement. Students, before discussing them one by one, let's understand what are rearrangement reactions first. Rearrangement reactions are a broad class of organic reactions where the carbon skeleton of a molecule is rearranged to give a structural isomer of the original molecule. This involves the migration of an atom or group of atoms from one position to another within the same molecule or from one molecule to another. There are two main types of rearrangements: intermolecular and intramolecular rearrangements. Here we see examples of both intermolecular and intramolecular rearrangements. The intermolecular Fries rearrangement involves the migration of an acyl group from one molecule to another, while the intramolecular Hofmann rearrangement involves the migration within the same molecule. Rearrangements can be classified based on the type of migration involved. Some rearrangements involve migration to electron-deficient carbon, while others involve migration to electron-deficient nitrogen. Each type has its own set of specific reactions. Further classifications include rearrangements involving migration to electron-deficient oxygen, electron-rich carbon, and even migration from oxygen to a ring. Each category encompasses unique reactions with distinct mechanisms. Let's delve into rearrangements involving migration to electron-deficient carbon. These reactions are crucial in organic synthesis and have various applications. The Wagner-Meerwein rearrangement is an organic reaction used to convert an alcohol to an olefin using an acid catalyst. This reaction involves the migration of an alkyl group to an electron-deficient carbon atom, commonly occurring in terpenoids. The mechanism of the Wagner-Meerwein rearrangement involves the protonation of the alcohol, followed by a 1,2 shift to form a more stable carbocation, and finally deprotonation to produce the olefin and regenerate the acid catalyst. An example of the Wagner-Meerwein rearrangement is the conversion of 2-methyl-butan-2-ol to 2-methyl-but-2-ene. This involves a 1,2 alkyl shift and subsequent elimination to form the final product. Applications of the Wagner-Meerwein rearrangement include the acid-catalyzed dehydration of camphenyl to produce xanthane, a key component of sandalwood oil fragrance. Another application is the acid-catalyzed dehydration of isoborneol to give camphene. This reaction involves a migration of carbon atoms to form a tertiary carbocation. The Wolff rearrangement is an organic reaction where an alpha-diazoketone undergoes rearrangement to form a ketene, accompanied by the elimination of nitrogen. This reaction is facilitated by silver oxide. The mechanism of the Wolff rearrangement involves the formation of a ketene, which can be converted into carboxylic acid, ester, or amide in the presence of water, alcohol, or amine. This reaction was proposed in 1935 as part of the Arndt-Eistet synthesis. Applications of the Wolff rearrangement include the conversion of acids to their next higher homologues, such as the conversion of 3-methyl-3-phenylbutanoic acid to 3-methyl-3-phenylpentanoic acid. Another application is the synthesis of mescaline, a hallucinogenic drug, from 3,4,5-trimethoxybenzoyl chloride using the Wolff rearrangement. The Benzilic Acid rearrangement involves the base-catalyzed reaction of alpha-diketones to form benzilic acid. This reaction is initiated by the addition of a hydroxide ion to benzyl. The mechanism involves the reversible addition of a hydroxide ion to benzyl, followed by a 1,2 phenyl shift and proton shift to form a resonance-stabilized carboxylate anion, which upon acidification yields benzilic acid. Applications of the benzilic acid rearrangement include the synthesis of citric acid from ketopinic acid and the rearrangement of furyl to benzilic acid derivatives. Further applications include the rearrangement of 9,10-phenanthronequinone and cyclohexane 1,2-diene to their respective benzilic acid derivatives. Now, let's explore rearrangements involving migration to electron-deficient nitrogen. These reactions are significant in the synthesis of various nitrogen-containing compounds. The Beckmann rearrangement involves the conversion of oximes to amides under the influence of acidic reagents. Phosphorus pentachloride is commonly used as a catalyst in this reaction. The mechanism begins with the treatment of the oxime with acid, generating a good leaving group. This leads to the formation of an electron-deficient species, which then undergoes migration. The resulting iminocarbonium ion traps water to form an amide. In stereochemistry, chiral groups migrate with retention of configuration. The rearrangement is highly stereospecific, with the anti-group migrating predictably. For example, plus methyl-3-heptyl-ketoxime rearranges to plus 3-acetamidoheptane with retention of configuration. The Beckmann rearrangement is used in the synthesis of various medicines, including paracetamol, benazepril, and olanzapine. This reaction converts 4-hydroxyacetophenone oxime to acetaminophen. Another useful application is the synthesis of caprolactam from cyclohexanone oxime, which is a precursor for nylon production. The Lawson rearrangement involves the conversion of acyl derivatives of hydroxamic acid to isocyanate, followed by hydrolysis to form amines. This is a variation of the Hofmann rearrangement. The mechanism of the Lawson rearrangement starts with the decomposition of the acyl derivative of hydroxamic acid in the presence of a base. This is followed by the loss of the carboxylate anion and hydrolysis of isocyanate to form the corresponding amine. Hydroxamic acid can also undergo the Lawson rearrangement to form primary amines under the action of strong inorganic acids. However, this reaction has limited synthetic importance due to the unavailability of hydroxamic acids. Rearrangements involving the migration of groups from oxygen to a ring structure are significant in organic chemistry. The Claisen rearrangement is specific to allyl-aryl ethers. Heating to 200 to 250 degrees C leads to the formation of O-allyl phenol. This pericyclic conversion involves the alkylation of phenol in the author position. The mechanism of the Claisen rearrangement involves a 3003 sigmatropic rearrangement, leading to an intermediate cyclohexadiene and proceeding via a cyclic transition state. This is a concerted intramolecular rearrangement. Evidence for the Claisen rearrangement mechanism was provided by performing the reaction with an allyl group labeled with 14C. The product showed the 14C labeled carbon exclusively bonded to the ring. This reaction was discovered by German chemist Rainer Ludwig Claisen in 1912. The Claisen rearrangement is used in the synthesis of orthoeugenol from 2-methoxyphenol. Eugenol is a volatile oil used as a desensitizer and carminative. The rearrangement of chorismate to prephenate is catalyzed by the enzyme chorismate mutase. This reaction is a key step in the shikimic acid pathway, essential for the biosynthesis of tryptophan, phenylalanine, and tyrosine. Thanks for watching. Kindly share and subscribe the channel. Take care. Goodbye.